Okay, here we've got an applied problem. It says, it's number 46 in the book. It says the yield V in pounds per acre for an orchard at age t in years, okay, is modeled by this function. Okay, so if you put a number in for t, that represents a number of years from now, I suppose. And V, the value of V that comes out, is the yield of the orchard per acre in that year. So if I put, 20 in for T, that would be like saying, what is the yield 20 years in the future? Okay, and then I could find that by computing this value of V when T is 20. Okay, now what they ask us to do, they say at what rate is the yield changing when, okay, and now they give us a couple of numbers to put in. They want to know 5 years, 10 years, 25 years. So, what the idea is here is that, say 5 years in the future, not only, are we interested maybe in the yield, but we might be interested in how quickly the yield is growing, okay? Because if, 5 years in the future, the farmer determines the yield is growing at a certain rate, maybe he knows, at what level he needs to buy new equipment or something. And typically I'd say this is probably usual, and that's the usual case, that if you plant an orchard, the trees are just getting bigger over time, so we would expect that this yield gradually grows. But they actually wanted to find the growth rate at a couple of different years in the future. Okay, so really, they call this V, but you can think of it as V of t. Okay, V is a function of t. Okay, and V is the yield. So if you tell me a time in the future, a number of years from now, I can compute the yield. Well, if we want to find the rate at which yield is growing, we need V prime of t. We need to compute the derivative of this. So we'll just do that. I take the derivative with respect to t of 7,955.6 times e to the power negative 0.0458 divided by t. Now actually, let me do one little rewrite here. This is all the power, that number over t. But I'm going to write that as the number times t to the power negative 1. Okay, you always know that when you're computing derivatives, it's helpful to write dividing by a power as multiplication by a negative power, okay, because our rules are phrased that way. Okay, so how do we compute this derivative? Well, I think it's probably a little bit more confusing because of the long decimal numbers that are involved, but if you look at what we have here, we have a constant that's being multiplied by this function, so we have a rule for that. Constants can be factored out of derivatives. Okay, so I can do this as a single step if I want. It might make things look a little bit clearer. Okay, nothing unusual there, just we factored out that constant. Okay, we'll deal with that later. And what about this derivative? Okay, well, we have to take the derivative of e to a power, okay? And the power, if it was just t, the derivative with respect to t of e to the t would be e to the t. Okay, but we're taking the derivative with respect to t of e to some other power. It's not just the variable here. So we have to use, yet again, this rule. And in this case, it's, if we're taking the derivative with respect to t of e to some power u, we get e to the power u times the derivative of u with respect to t, okay, because we're taking derivatives with respect to t. So the derivative is going to be e to the power u, this whole thing, okay, negative 0.0458 t to the power negative 1, okay, times the derivative of this power, right? We have to multiply by the derivative of u. Okay, well, and you can use the power rule to do that, and if you do, okay, right, what is the derivative of this? Well, this is a constant times t to the power negative 1. So we bring the negative 1 down. It's going to make it positive 0.0458 times t to the power negative 1 minus 1. Right? We always decrease the power by 1. So that's t to the power negative 2. Okay. So, well, we need to probably simplify this a little bit. Well, one thing we can do, we can combine those two numbers, the 7955.6, and I can multiply it by this 0.0458. Okay, and that gives me 364.36648. Okay, times t to the power negative 2. I might go ahead and put that right here. Okay, times e to the power negative 0.0458 t to the power negative 1. Okay, so it's actually kind of a complicated function. And of course next what they ask us to do, they want us to put some numbers in here, but it might take you a little bit of time to type it into the calculator. But you can check, and in this case, if we go to the calculator and put a number in, right, one thing they asked us, I guess the part A, was to find the rate at which the yield is growing, okay, 5 years from now. So if we put 5 in for t, go to the calculator and do that. So let's see here. Okay, when I put 5 in, type this in real quickly. I mean, it does take a minute to type this. You got to be careful that you have the powers right, that this whole expression is a power base e. But at the very end, I get 14 let's say about 14.44. Okay, 14.44 what? Well, the label is probably one of the more confusing things in here. Okay, V is yield, and we're talking about how fast V is yield per acre. We're talking about how fast yield per acre is changing per year. So if V prime of 5 is 14.44, that means that the yield is growing by 14.44 pounds per acre. Okay, that's what yield is measured in. We're talking about pounds per acre, but it's growing at that rate per year. Okay, so what that means is that going from the 5th year to the 6th year, roughly speaking, the yield per acre is going up 14 pounds, 14.5 pounds. Okay, so if the farmer has say 100 acres, it would be something like 1,444 pounds per year of growth. And what we see, we can go ahead and compute the derivative again, and of course this is one of the most time-consuming things, just to type all this into the calculator. You need to compute this expression now when t is 10. Okay, and when I do that, I get, let's see, I think I already did that, so I'll save myself some time. Okay, here I get 3.62, let's say about 3.63, okay, pounds per acre per year. Okay, so that means what? It means that in 10 years from now, the yield is still growing, but definitely not quite as fast. I mean, these orchard trees are getting bigger probably, but they might have gotten closer to their maximum size, so the yield isn't growing very much from year to year. And if I go ahead and do 25, well, then it's kind of what you'd expect. Probably, most fruit trees, for example, are pretty much at their maximum size after 15-20 years. So it's not growing too much here. It's about 0.58. So after 25 years, the yield per acre is only growing by basically half a pound. So half a pound per acre per year. Okay. So remember, these are growth rates. They're not telling us the yield per acre. They're just telling us how fast the yield per acre is growing, and we see what I would say is probably the expected outcome for an orchard, that as time goes on, the growth of the orchard slows down. At some point, it starts growing very slowly.